Morning, Mr. Kane.
Morning, Mrs. G. All right, so today we're going to start talking about Lewis structures, guys.
Okay.
We got a picture of Mr. Gilbert N. Lewis, an American chemist.
Finally, an American chemist.
And sometimes we call these Lewis diagrams or Lewis structures.
Okay.
But they're very important in chemistry because in the 1920s, these chemists started realizing that valence electrons were the most important thing for bonding. So basically what Gilbert develops is a way to draw the atoms very simplistically with their valence electrons.
Okay.
So he decides that the nucleus is going to be represented with the chemical symbol that you find on the periodic table.
Well, that's easy.
That's real easy, right? And that only the valence electrons need to be drawn. Since we have 4 sides on a symbol, top, bottom, left, right, he says we're going to do 2 dots per side, which would give us 8 valence electrons in total.
Okay.
And that kind of almost represents the S's and P's, doesn't it?
Yeah.
You know.
But not every atom has 8 to start with.
No, not every atom has 8 to start with. So we've got to actually show how that works,
Okay.
right? For atoms. So for atoms, such as hydrogen, which only has 1 valence electron.
1 valence, so you'd put a 1 dot.
So we would take out our little pen here and we draw 1 dot. Now, the standard is to start at the top and work your way around clockwise.
Okay.
Okay.
And then just spread out the dots and then partner up when you're forced to?
Right, partner. So we're using Hund's rule, so we don't
Yeah.
draw 2 dots on one side until
You have to.
we have to.
Okay.
So for beryllium here, which has 2 valence electrons, we draw an electron on top and an electron on the right side.
Okay.
Okay.
Going, starting at the top and going clockwise.
Right. For fluorine, I'd start at the top, I'd work my way clockwise with 1 on each side, and then I'd start doubling up, and that's all 7 valence electrons for fluorine.
Okay.
And finally for oxygen, I do the same exact thing, only oxygen has 6 valence electrons, so this is pretty much what oxygen looks like as a Lewis structure.
Okay. And with the criteria of starting at the top and working clockwise, everybody's Lewis structure for oxygen will look like that.
Exactly.
Okay. Set of rules.
Why don't you press pause and try this out. Alright, so let's see, for nitrogen you should have gotten this. For fluorine, you should have gotten this.
Which we just drew.
Neon, you should have gotten a full octet.
Right, because it has 8 valence electrons.
And for silicon, you should have gotten 4 valence electrons.
Ooh,
Now,
ions.
walking through ions really quick, the ions are already done for us on this page. Hydrogen ion, the cation loses an electron, so you don't draw a dot. What you do draw is you draw the hydrogen symbol in a square bracket and attach a 1+ charge to it.
Yep. And beryllium the same way, because those are losers.
Right, the cations lose, so they don't have any electrons to show, and you draw them in a square bracket. Now, at the bottom there, you see fluorine. Fluorine is an anion, it's a gainer.
Yep.
And
Started out with 7, right? Because
Right.
it was in family 7.
it's got 7 black dots,
Yep.
and it's got an X.
Okay, so it gained an extra electron.
And that extra electron is represented by that X. You don't have to draw it in red, but do draw the different shape.
Indicated different, yeah, it's an electron from somewhere else.
And oxygen does the same thing. It's got 6 valence electrons that are normally on it, and it's got 2 X's. Notice again, both my anions also are in square brackets.
Yep. If it's an ion, it's in brackets.
Pause, try these out. All right, there's your 3 answers. Nitrogen got 3 extra electrons, fluorine got 1, and neon doesn't form an ion. Trick question.
So let's see. We have learned how to draw the Lewis dot structure for standalone atoms and ions, and now we're going to learn molecules.
Ooh, molecules. So
Yep.
covalent compounds? Molecules?
Yeah, this one's going to be covalent, because if it was an ionic compound, you'd just have 2 pictures of 2 ions, like you just showed. Gather the information. So what information do we have to gather, Mr. King?
Well, the most important information that Gilbert thought.
The number of valence electrons.
Right? Okay. Then you got to arrange your atoms. Typical trick here, carbon, if you've got it, tends to be in the center. If it's not there, you could look for one with a small electronegativity. That tends to be in the center.
Oh, you want to pick your central atom here, correct? For this
Right.
number 2, yeah. It's either, if carbon's not there, it's going to be the lowest electronegativity, or it's going to be listed first, or it's going to have the smallest subscript.
Yeah, there's a lot of things to remember there.
Yeah, usually it's listed first.
Yeah. And another way to do it is to not pick your central atom. Halogens are not going to be in the center because they only bond once. Hydrogen also only bonds once. So those guys wouldn't go in the center.
Right, they'd just be branching off the central.
Yeah. What do you call those?
Terminal. I call them terminal atoms.
Okay, right. Then you draw bonds, chemical bonds. So shared pairs of electrons are represented by a dash. And a couple of rules for this. Hydrogen can only get one bond.
Okay, hydrogen's the only terminal atom that has an exception to the octet rule.
And then you distribute your dots.
The remaining dots.
Right, the remaining dots.
Okay.
All atoms must satisfy the octet rule, except for hydrogen, beryllium, and boron.
Right.
And then we verify our structures. Be sure that each atom follows the octet rule, and also double check that you drew only the amount of valence electrons that you predicted in step 1.
Okay.
Don't draw more and don't draw less.
Okay, so in step 1 you got a total number of electrons, which are dots or lines, depending on how going
Right.
through this. Right. And you got to make sure that you only use what you got, correct?
Correct. Yeah. Only use what you have. No more, no less.
Okay, step number 1.
So, step number 1, pick a central atom.
Step number 1, tally up the number of valence electrons. Carbon is in family number 4.
So, 4.
Chloride is in family number 7, but there's 4 of them.
So, 28. We get a total of 32 electrons in the tally.
Yes. Now, Mr. Kane, that number will always come out even, with the exception of nitrogen monoxide and nitrogen dioxide.
And I think we'll see those on a couple worksheets.
Other than that, that's always an even number.
So, second step, pick my central atom. Start to arrange them. So, I'm guessing that carbon has to be my central atom because chlorine can't be.
It's always a terminal.
It's a halogen.
Now, attach your chlorines to the carbon.
All right.
With a single line, and it branches off the central atom, not each other.
Okay, so I can't do another chlorine over here.
No.
By definition, carbon is the central atom.
Right. It branches off the central atom.
I want to be sure to keep carbon in the center.
Right.
So here we go. I now have 1 carbon and 4 chlorines.
And you just used
2,
8 electrons.
4, 6. Yeah, we just used 8 electrons. Now that's nice because carbon has 8 electrons now, right?
Yes.
32, so now I've got 24 electrons, right?
Yep.
Okay.
And those 24 get distributed around the terminal atoms first. And if there are any left over, they'll go on the central.
Okay. So 2.
And in pairs, probably
4.
because that's easy to count.
Now, would this be called a lone pair up here?
That's a lone pair, yep. Chlorine has 3 lone pairs and 1 bonded pair.
Okay, so 3 lone pairs and a bonded pair. So I just used 6, so now I have 18 electrons left.
Yep.
Okay, so 2, 4, 6 more. Now I have 12 electrons left. And 2 more to put them on. I've been putting 6 on each chlorine. That means that I'm probably going to run out of electrons by the time I finish with this chlorine.
And there are no extras,
6,
so nothing extra on the
0
carbon,
electrons.
which it wouldn't be anyway because carbon is always an octet.
Right. So let's double check things. This chlorine has an octet 2, 4, 6, 8. This chlorine has an octet 2, 4, 6, 8. The right-hand side chlorine has 8, 2, 4, 6, 8. And the top chlorine has 8, 2, 4, 6, 8. We've used up all the chlorines have octets. Carbon has an octet because 2, 4, 6, 8.
And you've got 32 electrons, so
And
this
if we
is a
count those up,
valid
that's
Lewis
32.
structure.
Yeah, and that matched my 32 there.
Yep, we followed the rules.
Very good, all 5 steps.
Water. Rule number 1, tally up the number of valence electrons in this molecule.
2 plus 6, 8 electrons is what we
so
got.
our structure will have 8 electrons. Rule number 2, pick your central atom. Well, hydrogen's always going to be a terminal, so it's definitely not hydrogen.
So I'm thinking oxygen is my central.
Correct. And rule number 3, branch off your terminals from the central with a single line to represent a pair of shared electrons.
So this is a pair, that's a pair.
Correct. Now you have to do the next step is to distribute the remaining electrons on the terminals first. But with hydrogen, you can't because it's happy, so they go on the central.
Okay. So we're going to put them on oxygen.
Yes.
So I put a pair here, and I put a pair here.
Yes. In paper and pencil world, that's a valid Lewis structure.
Okay. Now, Ms. G, I've got a question for you. If that was valid, is this valid?
Yes. For Lewis structure on paper pencil, that's a valid Lewis structure.
All right. And I'm going to ask you one more just because I know we're going to get this question in class. Is this valid also?
Yes. Same number of electrons, octet rule for oxygen, duet for hydrogen.
Okay. Yeah, it follows the rules.
On paper and pencil, those are fine. All right, carbon dioxide.
All right.
4 plus 12.
16 electrons.
And again,
An even
notice
number
it's
again.
even, yep, even number except for NO and NO2.
All right, Miss G, I think I know this. Carbon's got to be in the center,
Right?
and
branch
oxygen's
off,
going to be
yep.
on both sides.
Yep, branch off the terminals.
All right, so that used up 4 electrons, so I now have 12.
Distribute them on the terminals first.
2, 4, 6. That leaves me 6 left. Oh, I'm excited here. This is going to work out beautifully. Look, check this out. I've got no electrons left, and oxygen has 8, and oxygen has 8. I'm done.
Yep, no you're not. There's a problem.
What's the problem?
We have the right number of valence electrons established, but carbon has only 4 around it, and carbon has to have 8 around it.
Oh, the octet rule, right?
Yes, the octet
Okay.
rule.
Well, I'll just draw a couple more in then. So I've got -2 electrons. I can do this, right? It's like the national debt.
Yeah, no, I wouldn't suggest that. You cannot create electrons, Mr. Kane.
Oh,
sorry.
so it's got to be 16. All right,
Yeah,
let me get
we've got to do a little moving around of the lone pairs on the oxygens to make a double bond.
Okay, so I can just redistribute the wealth I already have.
Yes.
Okay. So if you said I have to take some from oxygen.
Yes.
If I take these 2 from oxygen and I redistribute them to carbon, that's not going to do any good. But if
Well, it's a start.
But if I share them
Share
instead,
them, yeah, share them between.
so don't redistribute to carbon, but share between carbon and oxygen. Now I've got 2, 4, 6. I've got 8 on this oxygen over here.
All right.
So there's still 8, 2, 4, and I've got 6 on this carbon.
Yes. So I would suggest you do the same thing on the right oxygen.
All right, so do it again. Does it matter which pair of electrons?
No, and I would also suggest paper and pencil because you are going to be erasing.
Pencil, really?
Yeah, I would advise a pencil.
Okay, pencil. So here we go.
This is going to take a lot of practice. There you go.
If I redraw those over here, now I've got 2, 4, 6, 8 oxygen on oxygen and 2, 4, 6, 8 on carbon.
Right, and 2, 4, 6, 8 on the other oxygen.
All right, now let's check. 2, 4, 6, 8, 10, 12, 14. Yep, there's 16 electrons drawn,
Yep, 16
which is what we
electrons.
decided in the first place.
Both oxygens and the carbon have achieved the octet rule. That's a valid Lewis structure.
Okay, so we can do something called a double bond if we have to.
Right. Only do the double bond if you come up short on the central atom.
Now, Ms. G, if there's a double bond, is there a triple bond?
Yeah, you could have formed a triple bond.
So there is ability to do multiple pairs. So
Yep.
there is a single pair using 2 electrons, such as the bond in hydrogen fluoride.
Mm-hmm.
There is a double bond using 4 electrons, such as the one in C2H4.
Yeah, the one we just showed you.
And there's a triple bond, which uses 3 pairs of shared electrons, or 6 electrons. And that exists, a good example is hydrogen cyanide.
Yeah, a lot of times the nitrogen will have a triple bond.
Now, something to talk about, 3 bonds is better than 1, right?
Yeah, well, 3 bonds would be stronger.
A single bond is weak.
Right, weaker, the weakest.
A double bond would be stronger, and a triple bond would be stronger.
strongest, yeah.
The strongest. Now, the length of the bonds should change, right? A single bond's kind of long.
A single bond is relatively long because it's just a pair of electrons being attracted by the protons. And then a double bond's going to get shorter because now you have 4 electrons being
Shared between
and attracted to the protons. And then a triple bond is 6 electrons. So they get really pulled in tight to the protons. So the triple bond is the shortest of the 3.
Okay.
Shortest and strongest, the SS.
All right. Exceptions to the octet rule.
There's always exceptions.
All right. Some elements can have fewer valence electrons. We mentioned this earlier. Beryllium likes to have 4.
Right.
At least in the examples we give.
Right.
Boron likes to have 6.
They can go up to 8, but they can also have 4 and
Right.
6.
Most of the time they'll have 4
Yeah.
or 6, at least for the examples we give.
Yeah, okay.
Other elements can have more valence electrons, such as sulfur and phosphorus, which can have up to 10.
Okay.
But sulfur actually can have 12 also.
Yep.
Selenium likes to have 12, and xenon even can have up to 14.
Okay.
All right, just for curiosity's sake.
Because the noble gases are inert, that means they are hard to form compounds, but they can.
Mm-hmm. All right. I think that's it for today.
We're done? Ooh,
We're done.
that's awesome.
See you later, guys.
Bye.